In the previous class, we have discussed something about the forced vibration, and the equation for the forced vibration is given by A is equal to F by M square root of 4B square P square plus omega square minus P square whole square, where B was the damping constant, that is B is equal to R by 2M, damping factor. And some three different cases we have considered when omega with the P, how it is exactly going to vary. And in that we have taken P very less than omega, P equal to omega, and P greater than omega. Three cases we have discussed, and during that one case we have considered when P square is equal to omega square, or P is equal to omega. So that we have taken it as the condition for the resonance for omega is equal to P. Now for that one, what all the conditions are required to meet out this, the exactly which is given by the force vibration. So those conditions are, the first one is, whenever there is a resonance, it is observed that the amplitude is going to be maximum, and this A to be maximum. So in this equation, the denominator factor, it should be minimum. When this is, the denominator is minimum, so obviously A is going to be maximum mathematically. And obviously in resonance, amplitude at resonance condition, amplitude is going to shoot up, it is a maximum. Now what are the two conditions? The first condition is the damping caused by medium must be minimum. Whatever the damping factor B is there, it should be minimum, B should be minimum. And second is that the applied force P must be equal to the natural frequency of the body which it is already oscillating. So P is equal to omega. So these are the two conditions. P is the external, the periodic force which we have applied, and omega, it is the frequency with which the body is already oscillating. Those should match. So these are the two conditions. So this mathematically we will just look out. Theoretical, okay. By the differential calculus, okay. So there is the rule states that the differential coefficient of a function will be 0 both at its maximum and at its minimum. The differential coefficient of a function, it is 0. It is 0 at both maximum and at minimum. So we are interested in the maximum. Therefore, the differential coefficient d by dp of the denominator, that is in this equation, the denominator which is given by 4b square p square plus omega square minus p square whole square. So we are taking the differential coefficient of that one and we are equating to 0. So after differentiating, it becomes 8b square p minus of 2p omega square p square, and 2 it comes here, is equal to 0, or 8b square p minus 4p into bracket omega square minus p square is equal to 0. If you take out 4p outside, inside it will be 2b square minus omega square minus p square is equal to 0, or the term in this, the particular bracket, is equal to 0, or rearranging this above equation, we get p square is equal to omega square minus 2b square. So the above condition what we have taken, the B must be negligible. So when B is negligible in this particular equation, what happens? When P is negligible, we get p square is equal to omega square, or P is equal to omega. So these above two conditions what we have mentioned here, these are the two conditions, condition 1 and 2. B should be minimum and P is equal to omega. So when B is small, P is equal to omega. So this condition is proved. Now the condition for the amplitude to be maximum. When the amplitude is going to shoot up, the maximum, that is which is given by A max. The above equation, the 14, the final equation, amplitude, it becomes A max is equal to F by M square root of 4 B square P square plus into bracket it is omega square minus P square. As omega is equal to P, it becomes 0. Therefore, it is F by M square root of 4 B square P square, or F by M square root of 4 B square omega square, because P is equal to omega, or F by M 2B omega. You call this as equation number 15. The state of vibration under the above condition is known as resonance. This is the condition for the resonance. The condition for the resonance, that the maximum amplitude A max is given by F by M 2B omega. Now, what is the significance of the resonance? See, at the resonance condition, we know that omega is equal to P. That is, the two frequencies of the are exactly matched and they are in same phase of vibration. This is very important. They are in same phase of vibration. Therefore, whatever the energy is supplied external, the P, external energy what we have supplied, it is completely absorbed by the system which is already oscillating with frequency omega. It means the whole energy is transferred, it is absorbed. Now, what is the definition of this word for the resonance? When the frequency of a periodic force acting on a vibrating body, external, it is equal to the natural frequency of vibration of the body, omega, the energy transfer from periodic force to the body becomes maximum. It becomes maximum because of which the body is thrown into a state of wild oscillation, and the meaning is amplitude is maximum and it is set into a maximum oscillation. So this phenomenon is called as resonance. In simple words, when P is equal to omega, we call it as resonance. It means when external periodic force, it matches with the natural frequency of the body which is oscillating, then the amplitude becomes maximum. So this condition is known as resonance. Even you can state in this manner also. So what are the examples? Examples are the Helmholtz resonator. So we will see it later. And next one is a radio receiver set tuned to broadcast frequency of transmitting station. So this we have observed. So whenever we want to set a few in any station in the radio, so we have to tune it. Maybe nowadays it is a digital. Earlier radio, if you observe, physically we have to tune it for that particular wavelength. For that particular, so there whenever the phase matching takes place, we are able to hear that particular radio station. It means with certain frequency, the radio waves are into the atmosphere, and the receiver, whatever the radio is there, radio receiver, if we tune it to that particular frequency, so we will get the maximum amplitude, in the sense the resonance takes place and we are in a position to hear that particular the station. Next one is the vibration caused by a excited tuning fork in another nearby identical fork. For example, there is one tuning fork which is already oscillating, and nearer to that one another tuning fork, if you bring a phase same, suppose 412 Hz is there, one which is already oscillating. So if you take another 412 Hz nearer to that one, so the prong which is oscillating, it will set the oscillation in the second tuning fork. So this is how the energy transfer takes place in the because of the same phase match condition, because both they are of same frequency. And one more is, in the microwave oven we have observed the microwaves of certain wavelength are emitted. So this is absorbed by the water molecules or the whatever the food the molecules are there, no? So that is absorbed, and by absorbing that particular wavelength, so these the food molecules whatever they are start vibrating and causing the cooking and heating up of the food. So whenever that energy matching takes place, the cooking will be very fast. That's why in the microwave the heating takes place very rapidly. Next, with these examples, next we will move to the sharpness of the resonance. What is how we are going to define the sharpness of the resonance? Before that one, we are supposed to know what is the meaning of tuning. Okay, it is a process of varying the frequency of the applied force to match the resonance frequency of vibrating body. It means we are once again making P equal to omega. P means the external the frequency. We try to match with omega. So that process we call it as tuning. Now what is the sharpness of resonance? The sharpness of the resonance, actually it is defined as change in amplitude to the change in frequency. Here at the bottom we have given the sharpness of resonance. In simple way to remember is, it is change in amplitude to the change in frequency. But how we are going to define? It is the rate at which the amplitude changes corresponding to a small change in frequency of the applied external force at the stage of resonance. So during resonance, at the time of resonance, the rate at which the change in amplitude takes place with respect to a small change in the applied frequency. So that ratio, so that particular we are going to call it, that is nothing but the sharpness of the resonance. As I said, it may be in simple words defined as change in amplitude divided by change in frequency. Next, at resonance, the amplitude of the vibration of the body is given by A max is equal to F by M 2B omega. This is previously we have derived in the resonance, which is known as, which is given by the equation number 15 earlier. Already we have taken A max is equal to F by M 2B omega. Okay. When there is no resonance, it is means for the forced vibration, this is the equation. A is equal to F by M square root of 4B square P square plus omega square P square minus whole square. And nearer to the resonance, what is nearer to the resonance? Omega will be equal to P. And in this equation, omega square minus P square is going to be 0 in above equation. Therefore, the above equation reduces to A is equal to F by M. It will be 2BP. This is nearer to the resonance, and the above equation is at resonance. Okay. Therefore, the change in the amplitude, what is the change in the amplitude is A max at resonance and nearer to the resonance, A max minus A. That is nothing but change in amplitude. So that change in amplitude may be calculated as, what is A max? A max is the above equation F by M divided by 2B omega minus F by M 2BP. So this is F by M 2B. If you take common, it will be inside 1 by omega minus 1 by P. It will be P minus omega divided by omega P. F by M 2B as it is. Rearranging the term, we get F by M P minus omega divided by 2B omega P. So this is equation number 17. Now, according to the definition, the sharpness of the resonance is defined as change in amplitude divided by change in frequency. What is change in amplitude? the above 17 divided by change in frequency. What is change in frequency? It is p minus omega. P is externally what we have applied, and omega is the frequency with which already the particle is oscillating, p minus omega. So p minus omega get cancels, and these two they get cancelled. We get f by m to be omega p. So if you observe carefully, the sharpness of the resonance is inversely proportional to the B. The meaning is that the B must be minimum. The damping should be minimum, then we get the maximum, the sharpness increases, and even the resonance also increases. Next one is the effect of the damping on sharpness of resonance. The damping factor, the B, along with the sharpness of the resonance. If you draw the graph of omega square minus p square, it is positive and this is the negative, along the amplitude, such type of the graph we are going to observe for different damping value. It is observed that for higher values of damping, that is 3, 2, okay, for higher value, that is for B is equal to 3, the curve is flat, means amplitude is not sharp, there is no sharp, it is a somewhat flat region. For B is equal to 3, it is called as heavy damping. For B is equal to 2, the second curve, it is a little bit sharp compared to that one. So it is moderate damping. For B is equal to 1, it is weak damping. And for B is equal to 0, there is no damping. Okay. So almost we are going to get the peak. And this for B is equal to 0, there is no damping, and it exhibits the value of infinity for the amplitude at resonance. So at some infinity, the amplitude will be maximum. Means practically it is very difficult to find out at what point we are going to achieve. So in general we can take it as at infinity we are going to get the maximum amplitude, the amplitude for that particular resonance condition. So this is the curve, it is flat for the higher values of B, and as B value decreases, the curve becomes sharp. That is the effect of damping on sharpness of resonance. Then what is the significance of the above? The significance of the above equation, the particular graph is when the frequency of oscillating body matches with the external periodic force. It means when P is equal to omega, we get maximum amplitude. At that time, the amplitude will be maximum. Okay. The rise of amplitude will be sharp when damping is very small. That is when B is 0. This is the significance what we can draw. That is when P is equal to omega, we get amplitude maximum, and at that time the damping should be very, very small. The damping has to be very small. So this is something about the significance of the sharpness of resonance. Next, the last one is the Helmholtz resonator. As I said, it will be discussed later. So what exactly this is the Helmholtz resonator is, or even called it as Helmholtz oscillator. So Helmholtz resonator or the oscillator, it is made up of a vessel, okay, maybe a metallic vessel will be there, such that it has two ends. One is opening, is small opening, we call it as neck. Other is with comparatively larger opening, it is called as the mouth. So neck and mouth it is there, and it has got the volume V, a known volume V is there. Now this neck region is placed near one's ear. We have to hold it against our ear to listen the notes, and this will be to the ear, and from here the input, the complex sound is passed, means sound is passed from the mouth. So this mouth, it enters here and it has got certain volume. and there will be a compression and rarefaction of the air molecule will take place when, okay, this P, the external, the note which is coming here, it exactly matches with the natural frequency of this resonator. It is of certain volume V and it has got certain frequency. So when P matches with omega, we get amplitude maximum, and that can be heard through this neck region. So whenever it is not matching, so we are not getting the maximum amplitude. So this is how the Helmholtz resonator is used to identify the quality of the musical notes. So usually the musicians, whenever they want to tune, so they go on adjusting the screw in such a way that at particular point, whenever it matches, they get the maximum sound. That is tuning. Initially, whenever the musical concern is there, they tune their musical instrument. So this is the Helmholtz resonator. It is used to tune the musical notes. Whenever the known frequency, for example, known note is required when it is passed through this Helmholtz resonator of a known frequency, then from this, the neck region, it is easy to identify the matching of the notes. So this is how it is usually used to analyze the quality of the musical notes. Here it is observed that in this particular equation, the omega square is proportional to 1 by V, the volume of the resonator. Okay, so or omega square is equal to K into 1 by V, where K is the constant of proportionality, or K is equal to omega square into V. Next, so the above, the Helmholtz resonator, it is for single frequency. For any one tone we are using. If at all we want to set it for different tones, at that time there is one more, the Helmholtz resonator, it is called as a tunable, so that, or adjustable. So it is given as, there is also an adjustable type of called as a universal resonator is there. So this universal resonator, it is such a way that it consists of two cylinders, one inside the other, so which can slide in or out to change the volume. Means two volumes, they will be in each other, where by changing their position, the volume can be changed. So likewise, it can be set for as a universal resonator.